Alright, this is my first real life tutorial, and what better way to start off than making an LED flash on and off with an 18F PIC micro. Designed for the complete beginner, I'm going to run through a bunch of components and development tools. I'll start off with my 9V battery. This is just a standard battery and a battery connector to allow me to interface it with my breadboard. And the end of the wire is tinned so that I can simply insert it. It's nice and sturdy. And yeah, so tinning just means that I've got a little bit of solder on the core of the wire. My 5V regulator, this ensures that I have a stable voltage for my PIC micro. And here I've got two 10 microfarad electrolytic capacitors. They're polarized. Notice on one side there's a band. This band has negative marks or minus marks, so that leg will be the negative pin, and the other side is unmarked. My PIC micro in some cases needs an external oscillator to run. Some PICs have internal oscillators, but here I'm using 20 MHz oscillators, and they can look like either one of these packages. In fact, they don't really vary from size to size. Just this is one type of package and this is another type of package, and you can get a range of oscillators in either type. Next is these two capacitors. They're ceramic disc type. They're rated for 22 picofarad. They're used to load up the crystal oscillator to ensure it runs accurately and correctly. There's a list in the PIC micro data sheet that will give a range of different oscillator speeds and different capacitance values. Next is the titanium capacitor. These are polarized, and there's a small plus on one side that indicates that that lead is the positive lead. These are used to remove transients on the breadboards or in any circuit. Transients are small signals, spikes, interference that sit on DC levels, and this capacitor will remove them and just short them straight to earth. And of course my PIC micro. Here I'm using an 18F 452. It's a 40-pin dip package, and that's why dip means it's got these leads on it, and SOIC is surface mount. And my 10K resistor is for the memory clear pin to connect it to 5V. And here I've got my LED and a 470 ohm resistor. This resistor is to make sure that the LED isn't overdriven. The bread and butter of any hobby electronics is the breadboard. As you can see, I can connect my IC, press it down nice and firm so that it sits flush and it feels like it's in place nice and secure. And each of these rows coming out are all shorted together, but they're isolated between each other. So from this pin here I can interface with it from any one of the three adjacent spots. These ones down the side are a power bus. If I just use this lead as an example, I won't be connecting 9V till later, I'll be connecting 5. But this power bus allows one whole column to be connected and the other column to be connected. So they're very handy for just having one reference to be able to just go straight over and connect it to your power source. To program my PIC micro, I'm using the PIC 2, and it's like $35 from Microchip. This arrow indicates like the first pin connection, and as you can see there's 6 here. I've gone to the liberty of making a little adapter cable so that I can use it in my breadboards. One is for memory clear, and that's a 1 on the far right there, indicating the green is for the to be connected to the arrow, and then each other one is identified and so forth. I'll go into more depth on the PIC micro later on the data sheet, but I can just plug it in like that, and on my breadboard I can just go to the pins. They're already in a known location for a 40-pin PIC micro, so I can program it straight up. And with that I can program any PIC micro that's in a dip package. And the other bit of bread and butter for development is wire. A handy hint: go out and grab some Cat 5 cable. It's really cheap, but make sure you get solid core. That means that the copper inside this insulation is one single core and not multi-strand. So now it's nice and sturdy. I can go from use it on my breadboards and not worry about the wires playing out and tinning the wire. And look how much you get. You just buy a meter and you'll be set for a long time. Wire cutters and an IC remover, very handy, because if you press these down nice and firm so they sit properly in the little clasps that hold the legs, they're very hard to get out. With this, seat it so that there's an edge under each side. Holding the breadboard, nice firm upward pressure, and I've taken it out with no damage to any of the pins. And I reckon you'd be hard pressed trying to get that out by hand without bending one whole end. All the pins would be facing in one direction.
Okay, so I've just followed the links, I've downloaded Swordfish, I've installed it, and I'm now playing around with the software itself. This button here is the new button, it creates a new document. So I've created a new document and I've saved it. I just saved most of my things in the bin directory that I'm not going to use too often later on, and then when I'm happy with it I'll put it into my own personal directory. Okay, so to start off with, Swordfish is structured in the way that you have to declare your device first and then your frequency of the PIC micro. And this is already in a megahertz range, so if I was using a 4 megahertz crystal it'd be 4, or if I was using the internal 8 megahertz oscillator on some PICs it'd be 8. And with PLL, well, I'll leave that and do it in another tutorial. Okay, so the dim allows me to declare variables and aliases. So in this case we have an alias of LED, and wherever the software finds LED, it's going to replace it with port B pin 0. So from here I can start writing my program, and to start off with I've used a while condition. So while true, this is an infinite loop. It's like writing while 1 equals 1. It'll never actually leave this loop and just keep cycling. The moment it gets to the end, it'll come back up. Okay, so the next line of code would be high LED. Bonus of using BASIC is that it allows you to use mnemonics that do what they sound like. So in this case, high bracket LED, it's actually going to make that pin an output and set it high. I'm then going to delay for 500 milliseconds, and then make the LED pin low, so it's going to flash on and off, and then delay for another 500 milliseconds. So this whole loop will take 1 second to complete, and it's just going to keep looping infinitely. Right, from here I'm going to compile the program. That's what these two little icons are, look like a refresh symbol, and you can get a couple of different options, but just hitting that will compile it for you. Going to my PIC2 software, I'm going to import the hex and find the program. It says hex file not loaded because it can't actually find the device. So what I'm going to do is plug in my PIC2, and I've already got it connected to my PIC on the breadboard with the required pins hooked up. And I'm going to go Tools, Check Communication. So now it's found the PIC2, PIC device found. So I'll re-import the hex. After you've located the directory that your file was in, you'll notice that the same file name but a .hex format will be shown in the folder. This is only here after you've compiled your project, and it's a machine code that Swordfish has produced for the PIC micro to perform the duties that you required it to do in your software. So if you do make a change in your program, make sure you recompile it and load the hex file again. Click Open to import it into PIC2, and then write to the device. Well, that was pretty quick, it's already done, and now my PIC micro is programmed. It has the whole Swordfish program loaded onto it, and it should do exactly as it's told, just flash on and off, and this whole loop will take 1 second. This is the 18F452 datasheet. Just download it from a link on my site, and you can also get it from the microchip site. A good way to browse around is to use the bookmarks. As you can see, it's listed all the way through all the different features, and I'm going to go straight to the pin diagrams, and I think it's on the next page you'll find the package that I'm using. So I'll just make this a little larger. As you can see, pin 1 is memory clear, And going to the next pin of interest would be 11, which would be VDD, which would be a positive power supply. Just note on the 40 pin PICs there are actually 2 power supply pins on either side. And going down on pin 12 is your negative, which is VSS, and oscillator 1 and oscillator 2, these are the 2 pins that your external oscillator connect to. So if I keep going down, pin 20, 21 is then on the lower right, going up to the negative power supply again, VSS, and 32 VDD. For programming, I generally haven't had an issue to date with just connecting these 2. Going up further, and here are your programming pins, PGD and PGC. So this is what I'd use with my little adapter I made, and just identifying which one's PGD, which would be pin 40, and just putting that into the breadboard, and PGC, same. From there you pick it to be able to identify what PIC micro is connected, if you've got power and memory clear as well. And you can just simply download your program onto the PIC.
Okay, so I just wanted to show you in real life what happened when I programmed my PIC micro. So I'll just unplug my PIC at 2. As you can see, I've got 5 connections: memory clear, PGD, PGC, positive and negative. Just showed you how to identify these from the data sheet, and these little connectors are very similar to the 5-pin one on the front here that I just snapped off a 40 row. They're just single connectors, wires soldered on the top, a little bit of hot glue just to make it a bit more sturdy, and now with that pin I can plug into anywhere I want on the breadboard, and whether it be 18 pin, 28 or 40 pin PIC micros, I can put it in my breadboard and program it. I'm making sure that number 1 lines up with the arrow because that's memory clear, and now I'm going to go to my software and program the PIC micro, and it's done. So that's how easy it is to program your PIC.
Okay, so now I'm going to cover how to identify what pins are what on the power supply or the voltage regulator. So I'm using the 7805, and I've just downloaded it from the link on my site. If I go down to page 2, it has a picture of the package I'm using, the TO20, and this flange on the back, or this is actually metallic. You can attach a heatsink onto it, but this is actually with the device laying down, and the square package is risen, like facing towards the top. So with it in that respect, the uppermost pin will be output, middle will be ground, and lower will be input. With that in mind, you can see on page 1 the fixed output regulator. This is just the basic circuit on how to use this device as a regulator. So the input, which will be my 9 volts, will go into that lead, the ground, and the output. And here are my 2 capacitors. But in my case, I'm using 10 microfarad for the nature of the circuit. I'll also briefly describe how I selected the 22 picofarad capacitors. I've just gone to bookmarks, gone down to oscillator configurations, and say the information starts about the different oscillators, different speeds. Scroll your way through till you find a capacitor selection for crystal oscillator, and just find the frequency that you're using and find something similar. So in this case I'm using exactly 20 megahertz, and it's listed here. And it says to use a 15 to 33 picofarad. In practice, I've used a 22 picofarad for every speed between 4 megahertz to 20 megahertz, and I haven't had any issues to date with using those speed that load capacitor. This is the wiring diagram for the circuit itself. Keep in mind though, with my software and in all of my video tutorials using this software, there's no power pins on the PIC micros. That's purely because the software just assumes that they're connected correctly, and just remember that 5 volts goes to both VDD lines, and you connect both VSS lines to earth. So going back up to the battery, which is this 9 volts here, this would be the red lead, and it'd be connected to the voltage regulator and this capacitor, the 10 microfarad capacitor, and the black lead would share the same common earth bus, one of the power rails. Okay, so this would be 9 volts coming in, and this would be a stable 5 volts coming out. And this capacitor will help maintain that even further as the load switches or the certain requirements of the circuit change. This capacitor will help maintain those changes and keep stability. It goes through a 10k resistor, which goes straight through to pin 1. Without 5 volts at MCLR, the PIC will not start as such. It will remain in a reset state. So it needs a high signal to actually enable it to begin incrementing the instruction clock. My oscillator is connected between pins 13 and 14, and on either side of it I've got these 22 picofarad loading capacitors, and they are both connected to the earth on the other end. These aren't polarized, doesn't matter which way they go in, but these are polarized. This line section indicates negative or the minus on the side of the capacitor. Port B pin 0 is the output for my LED, and it's running straight up to this 470 ohm resistor and then to the green LED, which is connected to earth. The LED itself, it'll be round, and there'll be a plastic flange around the bottom part of it. Now one side of that flange will be flat. Directly below that flange, that flat part, will be the negative lead or the cathode. So that'll be the lead that you'd connect to earth, and that's the line there on any LED diagram diode. The actual line that the arrow points to is the cathode. Okay, so with that out of the way, I'll just simulate the circuit with the program already loaded on there, just to show you what it's going to look like. And you can see it flashes once every second.
Okay, so I've assembled the majority of the circuit. As you can see, I've got my single core wire connecting everything up. This is my voltage regulator, and using the pin output I showed you earlier, I've got the input, the ground and the output all wired accordingly. One thing about these power rails I didn't mention earlier is that the power rail on these boards go from one half to the next half, like that. They're actually isolated in the middle. There's a larger gap here. There's no electric continuity between each rail over to the other side. And yeah, so I did have an issue with this one. I had this earth wire over here. It didn't work. Fault found it to be that was the issue. Alright, so the memory clear is just a 10k resistor going to 5 volts. I've got my oscillator wired up just like in the wiring diagram you can find on my site, and I've got my power rails or my power pins connected to the other ones, which connect to 5 volts and earth. So everything is set up and ready to go. Port B pin 0 is the output of that resistor, and just before I test it out, I just want to show you quickly an easy way to take the insulation off this copper wire. Using a Stanley knife and not cutting yourself, just score the wire around the outside and you can just pull it off, and there you have the copper exposed and it's nice and clean, and you're not going to wear off your teeth. Okay, so I'll plug in the battery, and there we go, it's flashing on and off, and this cycle takes 1 second for every flash. Now if it doesn't work, as I said earlier, you can fault find a couple of different things. Check the power first. Make sure you got 5 volts on your PIC micro across the positive and negative pins on your PIC. If you don't, go to your half split, your voltage regulator. Make sure that you got power from your battery coming in. Now if there's less than 7 volts on the power on the input, then the regulator won't be able to supply 5 volts. It's going to work hard, but it can't get there, and your PIC micro is going to have not going to have enough voltage. Other things to consider: your oscillator. If your oscillator wasn't sitting correctly, nothing would happen because the PIC micro wouldn't know when to execute the next cycle. So make sure that your oscillator is seated correctly, and that your capacitors and everything else are seated as well. Some other things, or one other point really to add, is that to increase stability and timing sensitivity of the PIC micro, you can use a 0.1 microfarad tantalum capacitor. These are polarized, and there's a very small positive symbol on one side. and basically you want to put that as close as you can to the power pins. So I'm just going to run it between positive and negative. And now that will remove all transients that the breadboard is creating that are running straight over to the into the PIC micro. Why are there transients? Because these rails here between pins act as small capacitors, and as things are switching on and off, an oscillator going over here, you're going to get little signals around the breadboard. So that's just one thing to consider, and it's good practice to put it in with every circuit. Alright, thanks for listening. I hope this helps someone out. Any other questions, have a look through the tutorial. You can find where to get all the parts and things like that. And yeah, have fun with PIC micros.